Okay, this is a video on temporal difference methods and reinforcement learning. I'm Chandra Sripada, and we've completed video 2, and now we are on to video 3. In this video, I'll use a TD algorithm to solve a particular version of a reinforcement learning problem. Okay, recall in the previous videos we introduced the calendar problem that has a structure like this. The reinforcement learning problem that we'll be talking about has a structure like this. There are many similarities, but there are some differences as well. Let's go through the components of a reinforcement learning problem. One thing that you have in common with the calendar problem is states, and they're depicted in circles here, just as they were in video 1 and video 2. Another thing you have is rewards, shown in red here, so that should be familiar to you as well. Here's something new, actions. In the calendar problem, you are essentially a passive agent transitioning from one state to another just with the passage of time. In a reinforcement learning problem, this is a fundamental difference. These lines over here represent actions, and there's more than one line that emanates from a state. In this particular reinforcement problem, I'm showing 2 lines emanating from every state, indicating that you can choose to go up or choose to go down. In other reinforcement learning problems, there could be multiple actions emanating from a state, sometimes substantial numbers of actions, but we're keeping things simple here. One thing to emphasize is, like in the calendar problem, you are not told the values in red at the start of the problem. More specifically, this is what you know when you are in a reinforcement learning problem. You know the state that you are in, whether you got a reward in that state and how big it is, and what actions are available to you in that state. So you're going to move through this state space each time just knowing the state you're in, the reward that you're gotten, and the actions available in that state. Everything else that you might know about the problem is something that you learn through experience. Okay, now we turn to Q values. This is another difference between the reinforcement learning problem, or this version of it, and our calendar problem we saw earlier. Q values are like state values. Remember, state values represented with the letter V were predictions. They were predictions of cumulative reward that you would get in subsequent states. Q values are different in 2 respects. First, they attach to state action pairs. So that's why there's 2 Q values here, because in this state there's that action and that action. So this Q value on the top is associated with being in this state and taking that action. This Q value is associated with being in this state and taking that action. There's no Q values here because there are no actions there. In addition, Q values are predictions of the cumulative Q value for a state action pair, SA, is a prediction of the cumulative future reward that you will get if you start in that state S and take that action and then subsequently behave optimally. So that's a little bit unclear what I mean by that, but that will become clear as we do our example. Your goal is to use experience to learn the true Q values for the problem or get reasonably close to them. Recall that was very similar to the calendar problem where your goal is to use experience to learn the true state values, V. Here are the true Q values for this reinforcement learning problem. So let's go through and make sure we understand why they are the true Q values. Look at this number 14. It's the Q value that attaches to being in this state and taking that action. So this value is saying that you will get 14 reward points if you are in this state and take this action and thereafter behave optimally. Is that correct? Well, yes it is, because if you're in this state and take that action, you can get 4 reward points for being in that state. Then you can take either this action or that one. And you can see that this one is the superior action, and if you do that, you'll get 10 reward points. So this Q value is reporting correctly that if you're in this state and take that action, 14 reward points is the maximum you can get. So on, for you can verify for yourself that the remainder of these Q values correctly report the future cumulative reward that you can get for each one of these states when you take the respective action. Okay. Now we turn to this super important question. Why would anyone care about having the true Q values? We've spent a lot of time learning about temporal difference methods that can get you the true or approximate the true state values or the true Q values, as you will see in the demonstration to come. Let's now ask the question, why do we care about this? The answer is, if you knew the true Q values, you'd know exactly how to behave optimally. So consider an agent in this state space. The agent, if an oracle whispered in the agent's ear what the true Q values were, the agent would know right away how to behave. Go up here, because the highest expected reward comes going that direction, and go up here, because the highest cumulative reward comes from going up in that direction. Q values are guideposts that tell you exactly how to behave. If you have the true Q values, you can behave in a utility maximizing way, a reward maximizing way. I want to emphasize again that an agent in a state space like this doesn't get this bird's eye view that we have right here. The agent is in a state, knows what reward they got in that state, and know what actions they have available in that state. Everything else the agent knows, they have to learn through trial and error repeated experience. This is a very simple state space. It would still take a lot of trial and error to know how to behave in a state space like this. What if we ramped up the complexity of the state space? You can see that any sort of method that gets you approximately correct Q values without going through a massive amount of data storage and data computation is an incredibly valuable method. So that's what is one of the major take-home points from this video series. Q values are incredibly important in state spaces that involve choice. And so a method like a TD algorithm that gets you approximate Q values is incredibly valuable as well. Here was the TD algorithm that we learned in considerable detail for the calendar problem. And it should be familiar from video 1 and video 2. Here is the TD algorithm that we'll use for the reinforcement learning problem. Notice it's incredibly similar. The big difference is that instead of state values V, we have Q values, and of course with Qs. And whereas V values attach to states, Q values attach to state action pairs. So basically everything else that we've learned before carries over to our reinforcement learning problem. Here is the example reinforcement learning problem that we'll be working with and going through one round of. Notice here that these are my initial assignment of Q values. In the calendar problem, I set all of the state values to 0. Why didn't I do that here? I could have. But it's easier for exposition purposes to provide an initial bias for the agent in each one of these states in terms of which action they'll choose. And so that's why I put a very small Q value on some of these numbers and zeros in other places. There's also an action selection rule that goes along with the RL problem, the reinforcement learning problem that we'll be looking at. That rule is choose actions with the maximum Q value. Now, it's not particularly clear why I have that action selection rule and how to use it. It'll become clear as we work through the example. So we always begin at the start node. And of course, we need to make a transition. A big difference was in the calendar problem, the transitions just happened for us. We moved from January to February to March. Here, we need to select a transition. This is the transition we make. That is, we started out here. Let me clarify it this way. We started out in this state with that action, and we transitioned to this state and this action. Why did we make that particular transition? And I've said it here. In the box, you see that the higher Q value is present here and here. That's why This state action pair was our initial starting point, and this state action pair is what we transitioned into. That's where this action selection rule becomes germane. It says choose the action with the maximum Q value. When we follow that rule, then we start out in this state action pair and we transition to that state action pair. So it's a little bit of an adjustment from the calendar problem where we start out in one state and we transition to the next. Here, we start out in one state action pair, that is this one in purple, and we've transitioned to the one in orange. Now for the terminology. S is the state that we were in. A is the action associated with that state. S prime is the state that we're currently in. A prime is the action associated with that state. Okay, more notation. QSA is the Q value associated with the previous state action pair. QS prime A prime is the Q value associated with the current state action pair. RS prime is the reward associated with the current state. With that notation in hand, it's an easy matter to calculate the prediction error and update the value of QSA. Again, RS prime is 4, QS prime A prime is 0.1, QSA is 0.1, so the prediction error is 4. I now substitute in that prediction error to this equation, 4. I set my alpha to be 1 to keep things simple. I realized that in the calendar problem I had used 0.5, but I want to keep things a little more simple here, so I'll use 1. The previous Q value, that is for QSA, was 0.1. And so my new QSA is 4.1, and I'm indicating that updating right up here. So now that update is complete, and I'm ready to make another transition. In your head, can you predict what that transition is going to be? If that's what you predicted, you're right. So this was my previous state action pair, and my current state action pair is now shown here in orange. It's this state and that action. Why this action? Because 0.1 is higher than 0. And again, I'm highlighting that I'm following this action selection rule. And then here's the terminology: QSA, RS prime, QS prime A prime. I substitute those values into these equations, and you can see the updating is going to be 0.1 is going to get updated to 1.1. At this point, I make another transition. And the transition that I make is to this node over here, which is a terminal node. I made that transition because 0.1 is higher than 0. What is the Q value associated with this terminal node because it lacks an action? Well, we give it, previously it was left blank, but we give QS prime A prime a value of 0. RS prime is going to be -4, and then QSA is 0.1. We substitute those values into the prediction error calculation as well as the QSA updating, and as a result, the Q value for SA transitions from 0.1 or gets updated from 0.1 to -4. Okay, from a terminal node, the transition is always back to the start point, at which point you'll make another set of transitions, as we did before. So recall, this is what the reinforcement learning problem looked like with our initialized Q values, and before we had done any learning from the state space. After just 5 iterations, this is what the reinforcement learning problem looks like. What you'll notice is that this upper half has already converged to the true Q values. Recall the Q value for this node, this state action pair over here, is correctly 14, and you can verify that the other values are also the true Q values. But look over here. These are not the true Q values, and in fact, they're identical to the Q values that were there at the start. Why is that? The reason is the way that the problem was set up, the agent never goes down to this part of the state space. So the agent can't learn anything on this part of the state space. The agent started out with a bias of going up, and that tendency to go up from the start node was never changed given the kind of learning that occurred over here. And so we need to change the rule that we follow just slightly. Our current rule is choose actions with the maximum Q value. But let's say we did this instead. We chose actions with the maximum Q value most of the time, but sometimes we explore actions with non-maximal Q values. If we did that, then we would sometimes go down to this lower part of the state space. We would learn about it, apply the TD update, the temporal difference updating rules, and then after a sufficient number of iterations, we would get the complete true Q values for the entirety of the state space. Turn now to probabilistic rewards. Thus far, we've been assuming that the rewards come with certainty. Recall that when we handled the calendar problem, we didn't need to make any modifications at all to deal with probabilistic rewards. If rewards come probabilistically, then the very same temporal difference algorithm in that case would converge to the true state values that reflect the expected reward. In the current case of reinforcement learning, the very same thing is true. You don't modify the algorithm at all. When you apply this algorithm in a regime with probabilistic rewards, then the Q values attaching to state action pairs will come to reflect the cumulative expected reward that you can get. So that's a nice feature of this algorithm. What about discounting? We saw that in the calendar problem, all you have to do to handle discounting is insert another term in the prediction error calculation. Whatever that discounting factor is, gamma, you multiply Q S prime A prime by gamma, and then the Q values that you will eventually, the Q values that get generated and updated via the algorithm will now reflect the discounted cumulative reward. So that's a nice way that a potentially complex calculation gets easily handled by the temporal difference algorithm. Okay, let's sum up. The temporal difference algorithm that we've learned can take a state space like this that has actions that you choose, and you don't know very much about the state space in the beginning. You just know what state you're in, what reward you got in that state, and how big that reward is, and what actions are available to you. But if you follow this pair of rules repeatedly, and you move around and learn from the state space, eventually you'll get the true Q values. Keep in mind that we are looking at this problem from a bird's eye perspective, but the agent inside the problem doesn't have that perspective. So these state spaces are challenging, and this is a small state space, and we can easily deal with one much larger. So an algorithm like this that can get you an approximation of the true Q values is incredibly valuable, because when you know the true Q values, like I said before, you know how to behave. Okay, that concludes video 3, and that concludes the entirety of the video series. I hope that was fun and informative.